Hey guys, welcome to another video. So today we continue on with the extension 2 topic of proofs, where in the last video, we basically covered on proof by contrapositives. We explored definitions for converse, equivalence, negation, and the counterexamples. In this video, we cover off on the proofs by contradiction, which is a bit more defined. The structure of the questions are a bit more predictable. So we'll cover a few typical questions that you see in past papers that off first, and then we'll do some sort of different ones towards the end. Not too hard today, but it's worthwhile covering just so you can get the structure. Guys, before I dive into it, please, if you haven't already done so, subscribe to the channel, like the videos, and tell your friends. Right, the theory for today, there's not a lot to write, so let's get it down. So proof by contradiction. Yeah. So basically, proof by contradiction is where we prove a statement is true by showing that the negation, so the opposite statement, the negation is illogical or false. Yeah. So normally what that entails is that as part of the negation, we assume something that is going to be true and then realize that, oh no, it's false, right? That's normally how we go about it. So that's all I was going to write. There really is no formulae or process. Let's get started. So I'll start with probably one of the two most common ones. You either prove this log thing is irrational, or the other most common one is proving root 2 is irrational, right? So for this process, very classical, let's assume we suppose that the opposite is true. So let's go there. All right, so suppose, now, sorry, let me just highlight the bit. So we're going to prove by contradiction that log 25 is irrational. So obviously the opposite negation event or statement is to assume that that guy, or suppose that guy is rational, right? Suppose log 25 is rational. Yeah, that is. So whenever we assume rational, in this case, it's less relevant, but there's always two points whenever we assume that it's rational, right? I.e., that guy there equals to a fraction, P on Q, say, where P and Q has two key elements. Firstly, P and Q are elements of positive integers, right? Yeah, technically they can be integers, but log's positive. Positive integers are safe, you know? And also, so maybe I'll put bullet points here, right? So first bullet point, where, maybe I'll do it like this. And then second bullet point, P and Q have no common factors. I think some schools call that mutually prime. Yeah, mutually prime, no common factors. And that's where, for the root 2 one, it's more important. For this one here, we can actually prove that it's illogical just by looking at it. Now, whenever you do this, right, we basically repackage this expression from log form to indices form, right? Where in indices form, basically the base of 2, P on Q is E power, and that equals to 5. Guys, mathematically, then we sort of Q power Q both sides. This side, the Q's cancel out, and you get 2 power P equals to 2 power 5 to the power Q, which is illogical. Now, you can say that because they're prime numbers, that statement would never be true, or you can just say, well, 2 to the power P is always even, while 5 to the power Q is always odd, right? So you go, which is up. So you can therefore contradiction, right? Because 2 to the power of p is always even, and 5 to the power of q is always odd. Yeah, therefore, statement is false. Therefore, log 2.5 is irrational. Yeah, simple as that. How many marks was that? 2 marks. Pretty straightforward from carrying about 2020, right? But you'll see this question as probably the most common contradiction question across all the past papers that I've seen. So common, log 1, because it's simple, right? Very easy. Mathematics behind it's quite strong, right? Pretty easy. Let's go on to our second most common one, but also for the next one, I thought I'd show you it because it's got a few more parts, which are not too hard, right? But just a few more parts to it. So the part 1 from Giraween 2022, classic. Prove that root 2 is irrational, right? And then there's a few more parts which I think are quite simple. Prove by contraposition that if n squared is not divisible by that, that's not, yeah, remember contrapositive, we basically assume the opposite of both sides, right? So if P implies Q, then Q prime or not Q implies not P, right? And then using part 1, prove that is rational. Okay, cool. So let's do this, right? So for part 1, prove by contradiction, right, that this guy's irrational. Okay. And then the next one, prove by contraposition, then prove this guy using part 1. Okay. All right. So suppose that root 2 is rational. Oops. So we do the same sort of assumptions as we did before. So that is, we assume that root 2 equals to a fraction or can be expressed as a fraction where 2 bullet points, P, Q are both positive integers, right? And P, Q have no common factors. So are mutually prime. Yep. Now, once you do that, it's all about just basically trying to prove, in this case, that both P and Q have a common factor. And for those that have done this before, that common factor is 2, right? So if we can prove that both P and Q are even, we're done. Because if it's even, then I could say that it's 2 times something. 2 is a common factor. That basically breaks this assumption, right? Breaks the negation case. So let's work off mathematically. Square both sides, right? So square both sides and you get what, 2 equals to P squared over Q squared. Yeah. Now, I must admit, leading up to here, right, there is a statement that says if P squared is even, right, then P is even, right? Sometimes your teacher doesn't want you to use that statement off the bat, so you'll need to prove it. Whenever you're proving root 2 and it's the first part of the question, you're allowed to use that statement, right? So, for example, if I times the Q squared up here, I'll go, therefore, P squared equals to 2Q squared. Now, the moment you realize that P equals to 2 times anything, right? It's even, right? P squared is even, right? The moment you realize that, so therefore, P squared is even. Yeah. And when that's the case, you can go, moment that guy's even, P is also even. Right? i.e. P equals to, let's say, 2m, where m is positive integer, right? So we re-express P as 2m, right? And then what we do, we plug, so I'm going to use a green colored pen, plug this guy back into here, And you go, therefore, 2m squared. Now, we've proved that p is even. If I can prove that q is even, then by contradiction, I've done it, right? Because they have a common factor. So once you sub that in, you got 2q squared here. So what's that? 4m squared equals to 2q squared. Therefore, q squared equals to 2m squared, right? So I don't really care about what m is. It's an integer. Oh, I'm at the bottom of my... So let me just move this up here so it fits nicely. Right, q squared equals that. Therefore, q squared is even. And that implies that q is even as well. Yeah, that makes sense, right? Q is even, q squared is even, and vice versa. Q squared is even, q is even, right? Now, given that, therefore, i.e., q equals to 2 times another integer, right? That is positive. Yeah, and the moment you realize this, guys, there's a 2 there, 2 there. They share a common factor, so therefore, contradiction. Yeah, P and Q have a common factor of 2. Yeah, therefore, root 2 is irrational. Yeah, admittedly, that is only 2 marks, and it feels like a lot of steps, but it's so predictable, right? It's copy and paste, so nothing too wow about that. All right, can I do part 2 over to the left here, right? Just so, because I have space there, and it doesn't actually take that long. So part 2, what am I doing? Prove our contraposition, right? Now, where's my 2 statements? I've got n is divisible by 18, n is not divisible by 6, okay? So this thing here, right? That thing there, that's like my P, and this thing here is like Q, right? So right now, P implies Q, so we state the contrapositive or contraposition that they want me to prove, where it's basically not Q, implying not P. So the opposite of Q is N is divisible by 6, implying N squared is divisible by 18, right? So in this case, so all we need to do is let n equals to 6 times some sort of multiple, right? K or something, right? Where K is a positive integer, right? Yeah. Actually, it doesn't even need to be positive, right? Just needs to be an integer. Yeah. Then n squared is equal to 6k squared. N squared equals to 36k squared. N squared equals to, now I'm going to take 18 out, right? Times 2k squared. And since you've taken the 18 out, yeah, and this guy here is obviously an integer. Yeah, since k is an integer, done. Right? Therefore, n squared is divisible by 18. Right? Therefore, contraposition is true, and therefore the original statement. Now let's repeat. Therefore, if n squared is not divisible by 18, then n is not divisible by 6. Yeah. So that question there, I mean, once again, very simple. All you got to do is, I mean, the hardest thing is basically stating the contraposition, right? So that guy there, right? We know that that is like Q prime, right? That is P prime, and that's how we do it. Yeah, and then part 3 is super easy, right? Because prove that that's rational. I've already proved that root 2 is rational. All I got to say is root 18 equals to simplify this, so it's 9 root 2. One's rational, one's irrational, has to be irrational, right? So very straightforward. Number 3, since root 18 equals to 3 root 2, right? Where 3 is rational and root 2 is irrational from 1. Therefore, root 18 is irrational. Yeah, simple. That's it, right? No need to sort of prove, that detail piece that we did previously. It's a 1 marker. That's 1 mark. That's it. So I thought I'd show you a question that was root 2 to start with, and there's a few extra elements that weren't that hard. Just hacked on for a 5 marker. All right. Let's do another question. Next one. Now, where was this from? Sydney Tech. I don't think this one's this one's not hard at all, right? It's 3 marks though, so relevant, but I don't think it's that hard. So, prove our contradiction. So for each irrational number, that number is also irrational. So I need to prove that the negation of this is illogical, right, or is false. So I'm going to assume, maybe I'll assume that this guy is rational, or maybe I'll assume the opposite, right? Always assume the back end, right? Assume that guy is rational, so opposite of that, and then show that S is rational. Yeah. So basically, the opposite of this, I want to prove that it's logical. So basically, saying right now, let's assume there's a rational number. If I assume that this guy's rational, if I can prove that S is also rational, then this whole thing is false, right? Yeah, this whole thing is illogical. So we start here, right? And suppose that, 2S plus 1 as a number is rational. Yeah, i.e. that 2S plus 1 equals, we've done this before, right? P on Q, where I feel like I'm copying. Can I just copy and paste it? Right? You and me, we got better things to do. Right? I'm just gonna go boom, boom, perfect. Right? Copy and paste. Yeah. Now, if that's rational, that fraction holds. I'm going to try to make S a subject, and while making S a subject, if it gives me another fraction, then it's also rational, and the whole thing's illogical, right? Yeah. So in this case, minus the 1 over. Common denominator. Right. So times top and bottom here by Q. Then you get P minus Q on Q. Divide the 2 over. Therefore, S equals to P minus Q on 2Q. Guys, that's it. I'm done actually, because I can demonstrate that for this one, this guy must be rational, right? Because P and Q are integers, right? Yeah. So when I say, I don't mean rational, I mean integers, right? They're integers. Yeah, must be an integer. When you subtract 2 integers, it's an integer. And the same with the bottom one here. Right, that must be an integer. Because Q is an integer. Yeah. I'll run it like this, better. Yeah. And therefore, if it is then, if it's an integer divided by integer, therefore S must be rational. Yeah, therefore contradiction. Right, because the question above, so it had for each irrational, right? So if I assume the second part is the opposite, right? It proved that the S was rational, right? Which is the whole thing is opposite. So therefore it's a contradiction. Therefore, repeat the question for each irrational number S, the number. The number 2s plus 1 is also irrational. Yeah, so this one here, the mathematics isn't that hard, but you're just gonna make sure that because it's a double statement, right? For each irrational, the number 2s plus 1 is also irrational. So we start with the second one, or suppose that it's rational, and then show that it's also S is also rational, right? Therefore, the whole thing's a contradiction, and therefore the statement's true. All right, next one. Now, I think the next one is a good classic question, but the harder type. So normally root 2 would be the irrational one, and that's usually worth 2 marks, as you see. Have you seen before? This one is 5 marks because it's a two-parter. Whenever the final goal is to prove that the cube root is irrational, that statement there previously in part 1 there needs to be proved, right? So we're going to prove that that's even. Now, it doesn't say, for the first part, it doesn't say which approach you take, but if it was left up to me, I'd say, well, it's in the format, right? Prove that. If this, then this, right? So it feels like a contrapositive sort of statement. So I'm going to go contrapositive on that and then go and prove part 2. So let's start. Feels like contrapositive, doesn't it? So if it's contrapositive, then the statement would be if P is odd, then P cubed is odd. Right? That's really the statement that I want to do. So once again, basically, right? If this is like my P statement and it implies Q, then this guy here would be my Q bar, Q prime. This guy is my P prime, right? Yeah, or angle, whatever notation you want to use. So if P is odd, so let P equal to 2m plus 1, right? Well, because I know 2m is even and then plus 1 is always odd, where m is just an integer, right? Oh, it's a positive integer. Let's go there. Now, if that's the case, right, then let's explore P cubed, right? So cube both sides, and I'm hoping that whatever number it is, and I'm pretty certain it is, that it has like an odd constant at the end. So then I could say therefore it's even. Therefore it's odd, right? So expand that using Pascal's. So it'll be this guy cubed, so 8m cubed plus 3 times that squared, so 3 times 2m squared times 1 squared plus 3 times 2m times 1 squared plus 1 cubed, right? So 8m cubed, what's that, 12m squared, 6m plus 1. I don't really care about that, but what's really pertinent here, what's really important is this plus 1 here, right? Because that makes it odd. Yeah, that makes it odd. So you can say, to make your teacher happy, factorize 2 out from this guy. So 4m cubed plus 6m squared plus 3m, right? And then plus the 1. Yeah, which makes it odd, right? Therefore, p cubed is odd. Yeah, because you can actually say that that's like 2n plus 1, right? Where n is also a positive integer. Yeah, then you've done it. So since you've proved, therefore, contrapositive is true, therefore, the original statement, so if p cubed is even, then p is even, right? Perfect, 2 marks. Contrapositive, and you know what, guys, I'm just going to move this down. Just want to move this. It's a bit too cutting into my space. Yeah, now I'm going to use that whole column there for part 2. So I need to now prove that cube root of 2 is irrational. You know what? Now that we've proven part 1, part 2 is exactly the same as when it was just the square root and not the cube root, right? So let's go there. So part 2. Suppose, spell suppose better. So suppose that cube root of 2 is rational. Yeah, that is, once again, guys, I'm going to borrow the same copy and paste if that's okay with you. Yeah, park it here. I'm going to park it out wide. Yeah, all right. I.e., the cube root of 2 is equal to p on q, where p and q are positive integers and p and q have no common factors, right? So right now I have this to go with. All right, what I'm going to do, times the q up and cube root both sides, right? So actually, let's cube root both sides now. 2 equals to p cubed on q cubed, times it up. Therefore, p cubed equals to 2q cubed. Now we go again, right? That guy's even. Therefore, p cubed is even. And from part 1, if p cubed is even, let's have a look. P cubed is even, then p is even, right? P is even, i.e. p equals to 2m, where m positive integer, right? And then what did we do? We plugged this guy into here, right? And then I'm hoping to get an expression that sort of says that q is also even, and then it's contradiction, right? So let's see, I've got 2m cubed equals to 2q cubed, expand that, that's 8. So therefore, q cubed equals to 4m cubed. So q cubed equals to 2 times 2m cubed, which is even, right? Therefore, q cubed is even. From part 1, q is also even. All right, therefore, q equals to 2 times n, where n was a Vincent. Guys, in this case, that's got a 2 there, it's got a 2 there, contradiction. Yeah, therefore, contradiction. Yeah, p and q have a common factor of 2. Yeah, therefore, cube root of 2 is irrational. Ration. It's very rational. Rational. That's better. How's that? So for this one, the only trick is to do part 1, right? Because once you do part 1, you have the extra. You previously couldn't write this statement, right? or this one. Yeah, but that all comes from part 1. Yeah. Hopefully that's okay. That's how you do the question where it's a cube root. You just go and need that extra element at the front. Guys, how's it going? Is that all right? So that's the structure for contradiction. I've got one more question, slightly different. It's actually not that hard. Once you sort of dig into it, you just need to know one, I guess, fundamental point. Let's do it. It's from Sydney Girls, 2022 past paper. So in this question, 2 marks, let A and B be positive integers, prove by contradiction that there are no solutions to that. So basically prove that the whole thing is flawed, right? What we do, we assume that there's a solution, and then as part of our assumption, the whole thing falls apart because it's illogical, right? That's really the key. So in this case, right, we go, suppose there is at least one solution to a squared equals 9b minus 6, right? Yeah, where a and b are positive integers. Yeah, here are that, where a and b are positive integers, right? All right. Now, once we've done that, I guess conceptually, this is how I'm going to play, right? If a squared, actually, maybe let me factorize 3 out. Therefore, a squared equals to 3 times 3b minus 2, right? Now, if that's a statement, it's really important for you to understand. So for a squared, right? How's this as logic? So if a has a factor of 2, say for example, right? If a has factor k, then a squared, which is a times a, would have to have factor of k squared, right? If k is a factor of a, then k squared must be a factor of a squared because k would be a factor of each one of the a's. Does that make sense? Now, that's important, right? That's important because right now I can see that a squared equals to 3, right? There's a 3 here, right? So then I need to confirm that this guy needs to be or needs to have a factor of 3. Needs factor of 3, right? Has to. Because if there's a 3 already, I need the 3 to repeat, right? I need a repeatable squared number that's a factor. Yeah, but we know, right? You can say here, right? Since 3 is a factor of a squared, yeah, 3b minus 2 needs to have a factor of 3 also. But, right? But we know that it doesn't because 3b minus 2 is 2 less than a multiple of 3, right? Because 3 times b is a multiple of 3. Minus 2, not going to have a factor. It's not going to be divisible by 3. Right? Therefore, thus, 3b minus 2 does not have a factor of 3. So does that make sense? So let me play that again. A squared, if a has a factor of k, then a squared must have a factor of k squared. In other words, whatever factor a squared has, it has to have a duplicate, right? And because they're all positive integers, if it's got a factor of 3, then it must have another factor of 3 somewhere, right? It doesn't have to be 3 exactly. It can be like 3 times another number. That's perfectly fine. right? But it has to have a factor of 3. In our case, 3b minus 2 is 2 less than the multiple of 3. Therefore, this guy does not have a factor of 3. Therefore, contradiction. Yeah, therefore contradiction. Therefore, a squared equals to 9b minus 6 does not or has no solutions, right? How's that? Is that okay? So in this one, we suppose that there was a solution and then sort of went, well, a squared needs to have 3 times another thing that has 3. The other thing, 3b minus 2, cannot have a factor of 3. Therefore, contradiction. Therefore, that guy has no solutions. Guys, I'm going to leave the video there. That's contradiction, and that wraps up this little burst of extension 2 proofs. If you like that video, please click on the like button, subscribe to your friends, also subscribe to the channel and tell your friends. I'll see you at the next video. Thank you.